Hello everyone. Welcome to episode 7 in the op-amp tutorial series, Lab Demos of the Inverting and Non-Inverting Summers. If you haven't had a chance to see the previous episodes, you can check them out on the channel. In the previous episode, we introduced the concept of summing circuits, derived the transfer functions for the inverting and non-inverting summers, and discussed the advantages and disadvantages between these two summer types. Today, we will be demonstrating the inverting and non-inverting summer circuits using an LM324 op-amp on a breadboard. First, we'll start with the 2-input inverting summer, then move on to the 3-input inverting summer, then do the 2-input non-inverting summer, and finally conclude with the 3-input non-inverting summer. We do both 2 and 3 inputs for both summer types because it's really the best way to see how the device works. When you transition from 2 to 3, you sort of get a better sense of how it works. Here is the 3-input and general solution we derived for the inverting summer in the previous episode. We use this to construct the circuit schematic and transfer function for the 2-input inverting summer, which is the first circuit we'll look at in the lab. Here's the general circuit for the 2-input inverting summer. So let's put some real values in for those resistors. Here, for each of the 3 resistances, we've put a 1K resistor in series with a potentiometer set to around 1K. Each potentiometer is a 2K potentiometer, so it can vary from around 0 ohms to around 2 kiloohms, and we can see what the effect of those varying resistances are on the output voltage. With the current pot settings, this is the equation for the output voltage, which simplifies to an output voltage of negative V1 plus V2. This is the simplest summer, as the weights are equal and the gain magnitude for each input is unity. The 2 signals we'll add together are a sine wave on V1 and a square wave on V2, both at 100 Hz. Now let's move over to the scope. Here we have the first input, V1, on scope channel 1, which is a sine wave at 100 Hz. And here we have the second input, V2, which is a square wave at 100 Hz. Now moving back to V1, we enable scope channel 2, which is connected to Vout. We see the output of the summer. It is inverting, and you can see evidence of this because the sine wave appears to be 180 degrees off, and the square wave seems to be lowering the input voltage lower, below ground. This is easier to see if we disable this square wave temporarily. Now it's just adding a sine wave to 0 volts, which just looks like the sine wave is inverted. We also see very clearly that the gain is negative 1, that both sine waves have the same magnitude. Bringing the square wave back, we move channel 1 over to V2 so we can compare the square wave with the output of the scope, and we can see the square wave's effect on the output. But to make it clearer, we'll disconnect the sine wave input, so now it's just a square wave on the input. And we see that the output is an inverted version of the square wave with the same magnitude as the input. Reconnecting the sine wave and moving channel 1 back to the sine wave input, we now adjust the potentiometer on V1 to see the effect of changing the input resistor has on the waveform. See that the sine wave magnitude is changing on the output, but the shift caused by the square wave isn't changing at all. So only the gain of the sine wave is affected by that resistance. Moving channel 1 back to the square wave, we now adjust the potentiometer on V2 to see the effect of changing the input resistor on the square wave input. See the shift caused by the square wave is changing, but the shape of the sine wave is unaffected. Finally, let's change the potentiometer on the feedback resistor to see that effect. And as we can see, this changes the global gain of the system and affects both waveforms equally. Now that we've looked at the 2-input inverting summer, let's take a look at the 3-input inverting summer just to further cement the mechanics in our minds. Here we have the 3-input inverting summer with 2K resistances for each input resistance, as well as the feedback resistance. Each 2K input resistance is made up of a 1K resistor and a 2K pot currently set to around 1K. Same as with our 2-input test circuit, the gain magnitude for all 3 inputs is unity in this circuit. We're going to do things a little differently for this 3-input version to better help visualize the effects of adjusting the potentiometers. All 3 input signals are periodic with the same period, but each signal is only present for 1/3 of the period. V1 is present only for the first third, V2 for the second third, and V3 for the last third. The approximate shapes of each waveform are shown here in red. V1 is roughly a square wave, V2 is roughly a triangle wave. It's actually the integral of V1, if it were more periodic. And V3 is roughly a double integrated square wave, or 2 parabolas joined together. So now let's move over to the lab to see this circuit in action. Here we have V1 on channel 2 of the oscilloscope. And here's V2. And V3. Let's move channel 2 of the scope back to V1 before revealing the output voltage. And here's the output voltage on channel 1. So we can see the output is the inverted version of the first signal, V1, in the first third of the waveform. Here we see that the output is the inverted version of the second signal, V2, in the middle third of the waveform. And finally, we see that the output is the inverted version of the third signal, V3, in the final third of the waveform. So altogether, those 3 signals are added together to create the final output waveform, which has all 3 in their respective time slots. Now we go back to V1 and adjust the potentiometer on the input resistance on V1 to see how that affects the output. And as we expect, it changes the gain of the V1 portion of that signal only. The other 2 portions of the signal remain the same. Moving on to V2 and adjusting the potentiometer on the input resistance to V2, we see it only affecting the second signal and not the first or third portions. And finally, adjusting the potentiometer on V3, we see only the portion of the waveform on V3 changes. The other 2 remain the same. Now that we've explored the inverting summer, let's move on to the non-inverting summer. Here is the 3-input and general solution we derived for the non-inverting summer in the previous episode. We used this to construct the circuit schematic and transfer function for the 2-input non-inverting summer, which is the next circuit we'll look at in the lab. Here's the general solution for a 2-input non-inverting summer. Now we put in actual resistor values. Here, for each of the 3 resistances, we've put a 1K resistor in series with a potentiometer set to around 1K, just as with the inverting summers. With the current pot settings, this is the equation for the output voltage, which, reducing down and simplifying, we get an output voltage of V1 plus V2. This is very similar to the inverting summer we just did, except that the gain is positive rather than negative. Same as before, we'll add together a sine wave on V1 and a square wave on V2, both at 100 Hz. Now let's move over to the scope. For reference, here's V1 on channel 1, a sine wave at 100 Hz. And here's input signal V2, a square wave at 100 Hz. Moving back to V1, we display Vout on channel 2. Here we can see it's non-inverting. The output follows the input when the square wave is low, and gets bumped up in the same parts that the square wave showed up before. To show it more clearly, let's disable the square wave briefly, which effectively sets V2 to 0 volts. We see the sine wave input and sine wave output on top of each other, looking very close to the same value. Re-enabling the square wave, and moving channel 1 to V2, we can see that the square wave lines up with the voltage shifts upward. Now if I disconnect the sine wave as I did before with the inverting summer, that presents an open circuit at V1. This produces a much different effect. The sine wave does indeed disappear from the output, but the square wave becomes much more amplified. This is because by disconnecting V1, we've effectively infinite valued its input resistance, and so that affects the gain for V2. To get the effect of nulling V1, like we did with the inverting summer, we have to short that input to ground, rather than just disconnecting it from the function generator. Now with V1 set to 0 volts, we see just the square wave input, and the output looks the same as the input square wave. Disconnecting the V1 input from ground and reconnecting it to the sine wave signal to get the circuit back into the previous configuration, let's see what happens when we adjust the potentiometers. First, looking at V1 and adjusting the potentiometer in series with V1, we see the sine wave portion increase as I decrease the input resistance, and the square wave portion decrease. So both are changing in opposite directions. This is one of the fundamental differences we've discussed in non-inverting summers, that changing one of the resistances affects the effective gain of all the inputs. Looking at V2 and changing its potentiometer, we see the same sort of thing happens with the square wave. Increasing the resistance decreases the square wave magnitude and increases the sine wave magnitude, and vice versa. Finally, we can change the global gain setting resistor's potentiometer, and we can see by increasing that resistance, we reduce the gain for both inputs, and by decreasing that resistance, we can increase the gain for both inputs. Thus, with a combination of changing the global gain and changing the relative input resistances, we can set the weights of each input in the same way as the inverting summer, though with a few more steps. Now that we've looked at the 2-input non-inverting summer, let's take a look at the 3-input version to get a better feel for how the non-inverting summer works. Here we have the 3-input non-inverting summer with 2K resistances for each input, a 2K resistor for RG1, and a 1K resistor for RG2. Each 2K input resistance is made up of the same 1K resistor and 2K pot as we did before, with the pot set around 1K. Now, simplifying the equation, we get a gain magnitude of 1 for all 3 inputs. Note we had to increase the global gain to a factor of 3, whereas before it was 2, to maintain the unity gain for all 3 inputs. We'll have the same 3 signals as with the 3-input inverting summer, separated in time the same way as we did before. Now let's move to the oscilloscope. As a quick review, here's V1 on channel 2 of the oscilloscope, here's V2, and here's V3. Back to V1, let's display the output. And here we see that since it's non-inverting, the first signal lines up with the output in the first third of the waveform. Now I'm going to adjust the potentiometer of the first waveform, V1. And we see that increasing the resistance on V1 decreases V1, but increases both V2 and V3. Similarly, decreasing the resistance on V1 will increase V1, but decreases both V2 and V3. Here we do the same thing on V2, which changes V1 and V3 similarly. And we do the same with V3. So we can see a stark contrast between this non-inverting summer behavior and the inverting summer behavior, where modifying one signal's series resistance affected the gain only of that signal's, and the other two remained the same. Whereas here with the non-inverting summer, modifying one signal's series resistance affects the gain of all 3. And so it becomes harder to adjust the weights if you want to keep the gain for one signal static. And so to keep the gain of one of the input signals static, you often have to not only adjust the input resistances, but compensate for those changes by adjusting the global gain of the circuit. That concludes this episode. In this episode, we demonstrated the 2 types of summing circuits in the lab with the LM324. In the next episode, we will be exploring setting the non-inverting input to a non-zero voltage in inverting amplifier circuits and introducing the op-amp differential amplifier circuit. Thank you for watching the video. If you enjoyed it, please like, share, and subscribe. See you next time.